Hey guys, in this video I'm going to be talking about how to find the area of a sector and find angular and linear speeds. So first we're going to start reviewing area of a sector. So remember, this is from geometry. So remember from geometry. A sector of a circle is a region bounded by a central angle and its intercepted arc. So if we have a circle, here's the center, here's some angle, theta, the intercepted arc is here, so if I shade it, this is going to be my sector. So we can label this a few different parts. So this angle's theta, like I said. We could call this circle P and have this be, well, it really doesn't matter. We got the radius, the angle, and this is circle P. So the area of the sector, actually let me rephrase that. So the ratio of the area of a sector and the area of a circle is equal to the ratio of arc length to circumference. Knowing that these two ratios are equal, we can use it to solve for the formula for area of a sector. So we could call that just A. How do you find the area of a circle? Hopefully you remember is pi r squared. How do we find arc length? Well, we talked about this the other day. It's theta in radians times r. So I'm just going to refresh your memory real quick that this is going to be in radians. So maybe take a side note. And then circumference, if you forgot, is 2 pi r. And then we can multiply both sides by pi r squared to get it out of the denominator. And so these will cancel and we'll be left with r. And then pi's will cancel. And so this is going to be area is equal to theta times r, so r squared over 2. So this right here is the formula for area of a sector. So, knowing this, I could give you an example. If we know, so find the area of a circle, or sorry, not circle, sector. If we know that theta is equal to 50 degrees and the radius is equal to 6 meters. So we can just use this formula. So before we use the formula, this needs to be in radians. So if we remember from yesterday, 50 degrees times, since degrees is in the numerator, we're going to put 180 degrees in the denominator and pi in the numerator. And so degrees will cancel, and 50 over 180 reduces to 5/18. So this is it in radians. And now we can just use our formula. So remember, I really recommend writing down the formula every time. So area is going to equal theta times r squared over 2. So now substituting in what we know, we're going to have, since theta is a fraction, I'm going to just say 1/2 times theta, which is 5 pi over 18, times our radius, which is just 6 squared. So now 6 squared is 36, and 36 times 5 is 180. Okay, don't forget my pi. And 2 times 18 is 36. Could have simplified that earlier. So that means that 180 divided by 36 is just going to leave us with 5 pi. So here's our exact answer, and then using a calculator, 5 times pi, that's approximately 15. We'll round to the nearest tenth, 0.7, and that's going to be meters squared, because remember our radius is in meters, and we're finding an area, so we have meters squared. And I'm just going to write a little side note. Remember that this is the exact answer, and this is the approximate. So the area of a sector isn't too bad, it's just really plug and chug. Now we're going to talk about linear speed and angular speed. So first let's talk about linear speed. I'll color code. So linear speed is going to be the rate an object moves along. So the rate an object moves along a circular path. So the rate an object moves along a circular path, this can be represented by v equaling s, or arc length, divided by t. So we could also just say v equals, remember, arc length is the radius times theta over time. So that's linear speed. Then there's angular speed. Angular speed is going to be the rate an object rotates around a fixed point. So a way to think about it is like how fast an angle is changing. Or the speed of an angle, even. Which makes sense because it's angular speed. So the formula for this is represented by omega, which looks like a W. And that equals theta divided by time. So let's do an example of this to help clarify. So example. A typical vinyl record has a diameter of 30 centimeters. When played on a turntable, the record spins at 33 1/3 revolutions per minute. So revolution is going to be going around once. So in 1 minute it spins around 33 times and then gets about 1/3 of the way. So for part A, we are going to determine the angular speed in radians per minute. Find the angular speed in radians per minute of a record as it plays. And let's round to the nearest tenth. So I would start with the formula, which is going to be omega equals theta over t. And when I say omega, that just represents angular speed. So this is just saying angular speed is theta divided by time. So the thing is, what is theta? Okay, well, theta is going to be the angle, right, in radians. So here's my record. Okay, it goes around 33 1/3 times. I'm not counting. So it's going to be 33 1/3 times. How many times does that happen? Well, we're doing radians, so one revolution is going to be 2 pi. So if I multiply 33 1/3 times 2 pi, that's how many revolutions? Oops. In 1 minute. So then we could just do this whole thing in our calculator actually, so why don't we do that? So 33 1/3, which is what? So 3 times 33 plus 1, so that's going to be 100 thirds times 2 pi. So I guess that's still what it equals. So it's approximately 209.4 radians per minute.